This is the first in a series of videos that I'll be making documenting my research towards obtaining a master's degree in pure math. So for this first video, I'd just like to motivate and maybe explain a little bit about the topic that I'll be covering in the next videos. This series should last about a year or so, hopefully, which is because in a year I'll be defending my thesis. The area of research is mathematical analysis. So the area is analysis. And for those that are unfamiliar, this is the study in math of things that involve inequalities. So we have lots of inequalities. We have limits. So we take limits as things tend to infinity, tend to zero. We deal a lot with functions, bounds, upper bounds, lower bounds on things. And so this is where the research is going to be situated. In particular, differential equations. And we're interested in the linear kind. So a differential equation is something that looks like, maybe for those that are familiar with a derivative, something like this maybe, where f is a function, g is a function, and we are given g, and we would like to find f. So we'd like to find the function, a function that satisfies an equation that has to do with its own derivatives. So that's a differential equation. These can take a more general form. So the linear kind are usually expressed like this, where this m is an integer, and this alpha is a multi-index. So I recommend reading the Wikipedia page on multi-index to get insight onto what that is. And over here we have coefficients and the differential part here. So this is just a partial derivative with respect to this multi-index. And this is a constant that depends on the multi-index. We can also have variable coefficient linear partial differential operators where we add an x here. So that would look something like this. So this is the linear partial differential operator, and it would act on a function. So we can put this whole thing here, acting on a function. We could say it's equal to another function, and we could give f and ask what is u. So these are the kind of problems we're interested in. But not just solvability right now. I'm commenting a lot on solvability, which is the problem of trying to determine this function u, given this equation. But there are other questions. So this is the question of solvability. We have local and global solvability, so that has to do with where we determine u, if it's just locally or on its whole domain. This is solvability. And another interesting question that we can ask is on, let's say regularity. So regularity is asking, okay, given that we have a solution, how nice is it? So, for example, our solution can be, by nice we usually mean in what class of differentiability is it? So is the u that we found just continuous? Is it in C0? Is it in C1? Is it in C2? Is it smooth? Does it have all orders of partial derivatives and they're all continuous? And these are the questions we ask. And later on, we'll find that the worst possible case of regularity isn't even being C0. There are classes of functions. There are objects that are more general than even, well, first of all, there are functions that aren't continuous. They're just regular functions. But there are things that are even more general than functions, which will serve as solutions to differential equations, such as this one. So regularity is another objective of ours. Determine the regularity of solutions. Two objectives, regularity and solvability. Okay, So these are our objectives. And we have a few tools that will be fundamental when we solve these kinds of problems. And these are measure theory and distributions. So measure theory is more useful technically. So it offers us many useful lemmas which we can use in our computations. The very notable one is the dominated convergence theorem. Which allows us to do operations such as this one. We have a limit and an integral, and we would like to exchange that limit with the integral. It gives us conditions under which we can perform this kind of swap. Yes, and where this integral, these integrals are actually the Lebesgue integral, so it's also measure theory also gives us a more general way to integrate, which is also very useful. And we also have the theory of distributions. So the theory of distributions doesn't only give us, isn't most notable for it giving us technical tools. It in fact changes basically everything we do, because the solutions, the distributions are usually where we search for solutions. So the theory of distributions is very fundamental. And what it does is it generalizes the class of functions. And more importantly for us, it generalizes the class of functions which make sense as solutions to differential equations. So not only does it give us something more general than functions, but everything in this class, in this larger class, can be differentiated arbitrarily many times. So we can always take an operator like the one above here. You can always take an operator that looks like that and apply it on a distribution U, and that will always make sense. So it's a very nice space to search for solutions. The problem is that in the real world, people might want smooth solutions. So if we have a differential operator P, applying on U, giving an F where F is given, and so is P, and we want to find U, let's say through mathematical theorems, we can deduce that U is of a given type, or let's just say we know it exists. We have existence of U, but U is a distribution. So this is a notation for the space of distributions. So U is a distribution, but we want a smooth solution. Why would we want a smooth solution? Well, one reason is that many theorems in math require as a starting point, as a hypothesis, that your U be smooth. So if you're solving a differential equation and you want to apply the solution, so you have a solution to a differential equation, and that's not the end of your problem. Let's say you still need to apply that. You need to take it and apply it in some other theorem, and that'll give you what you want. Then it's nice to have a C infinity solution, because there are many theorems that require the input to be C infinity. Well, another motivation for trying to determine if U is smooth is that if you're more of an applied person, in numerical analysis, in numerical methods for solving PDE, some of them have much faster convergence if you a priori know that U is smooth. So that U is smooth implies faster convergence of numerical methods, depending on the method. So I'll give an example. For example, the spectral method. If we can determine that the solution is of a certain regularity class, then we can have faster convergence of the method. So I think I can give an example of distributions. I won't define what they are now, but well, I guess I can give a little bit of an intuition. So a function, let's say a function from R to R, intuition in one dimension, looks something, let's say a continuous function might have a graph like this, and its correspondence of points in the domain to points in the codomain. That's what a function is. So a distribution generalizes this concept by making this a little blurry. So what I mean by that is, instead of associating to each point in the domain a point in the codomain, we associate to each function, which we call a test function. So let's say we have like a function something like this. We associate to every one of these functions a value. So associate to every one of these a value, and that value will correspond to a weighted average. You can think of it like a weighted. This is very intuitive. You can think of it as a weighted average of the values of what would be the function according to your test function, which is this blue curve. So in this case, you would multiply at every point. To get this value, you would essentially integrate the function which is given at every point by the multiplication of this point in blue with, let's say, this point in green, and then at this point it would be this point in blue with this point in green, and so on. And so you would integrate over the support of this function blue. And that would give you forever. So this association of every one of these test functions with a value, which is given by a sort of a weighted average, this defines a distribution. And it defines objects more general than functions. An example, which is the classic example, I guess, is the Dirac delta. So you have a function that, let's say, at 0 it equals infinity. That's what people say, I guess. Physicists would say that the Dirac delta at 0 equals infinity, and everywhere else equals 0 if x isn't 0. So that would be the informal definition, but you can define an object like this formally using distributions, and the way you do that is for the distribution would be defined as basically every test function that has support that doesn't intersect the origin. So for these test functions over here, you would return 0. So the value associated with these test functions is 0. But as soon as you get a test function whose support intersects 0, this would be a non-zero value. It would be associated to a value that's non-zero. So anyway, that's how you would go about defining an object that is not a function, but it is a distribution. And you can differentiate objects like this, and these objects are derivatives of other distributions, and so on. So that's why we need distributions. This is where we search for solutions. It's often easier to search for solutions in distributions. So again, going back to the question of solvability, we search for solutions to distributions. If they exist, then we determine their regularity. We say, okay, they exist, but we would like them to be nice. We would like them to be at least functions, and if we can, smooth functions. Okay. So another benefit of using distributions. Is that most operations that you're used to, they transfer nicely over to distributions. Especially one very important one, which is the Fourier transform. So the Fourier transform is very nice for us because of the properties that it has when it interacts with linear partial differential operators. When it interacts, especially with derivatives, turning derivatives into polynomials, and convolution into multiplications, that sort of thing. So convolutions turn into multiplications, derivatives turn into polynomials. So it's useful for these kinds of properties, and these things are preserved when you define it quite naturally in the realm of distributions. And in fact, we also have some theorems that not only is the Fourier transform similar operationally, but it's similar in terms of the theorems that you obtain. So for an example, a very nice example is the Paley-Wiener theorem. Which qualitatively, it would state that, I guess I'll talk about the classical case first. So in the classical case, if we take the Fourier series of functions, there is an association. There is an association between regularity of a function and association between the regularity of the function and the decay of its Fourier coefficient. So I'll denote that by f hat, the decay of Fourier coefficients. We have that also in the context of distributions, except so the regularity of f, I'll substitute these by u. It's more conventional to call distributions u. And so the regularity of u might be determined, might look something like saying that u is an analytic function, a complex analytic function. So this makes more sense if I actually state the theorem, which I won't do now, but it has to do with the Fourier Laplace transform. So regularity in the context of the theorem can mean complex analytic, or it can mean just regular smooth, just C infinity over Rn. And the decay of the coefficients is simply fast decay. I mean, it's the same thing as essentially the same definition as fast decay of the coefficients of the Fourier series. In fact, it can also mean having compact support in the case of distributions, because that's essentially the fastest distribution can decay is having compact support. So yeah, we have so these two concepts are very strongly intertwined, and exactly how that happens is given by the Paley-Wiener theorems. And so these kinds of theorems, they help us with the problem of determining regularity of solutions. So what does this have to do with regularity? I can give an example in the classical case, which is the linear partial differential operator L, given by d dx plus alpha d y, where alpha is a real number. So we have this linear partial differential operator, and we're searching for solutions u, where u is periodic on R2. Okay, so this is where we're searching for solutions, and we can actually characterize. We can characterize when this operator is hypoelliptic. So that's, I think, the first time I've said that word, hypoelliptic. So hypoelliptic is so we can determine that a solution is of a certain regularity class. But how do we determine that an operator is of a certain regularity class? Well, that's what the definition of hypoellipticity does. It says that an operator, L, is hypoelliptic. You can think of that as being essentially regular. If we have a case like this, where let's say U is in a predetermined regularity class, it's pretty low, let's say it's a distribution, and F is, let's say, infinity, so F is very regular. So if we're in a case like this, then that implies that U also must be regular. So it's an operator that transmits the regularity of F to U necessarily. So that's what hypoellipticity is. It's an operator that behaves nicely with respect to regularity. And we can determine whether we can actually characterize the hypoellipticity of this operator based exclusively on what, on alpha. And so the theorem is as follows. So L is hypoelliptic if and only if alpha is irrational and not a Liouville number. Now, a Liouville number you can essentially think of as a number that is very well approximable by rational numbers. So we have the rational numbers. Then we have the so you have the rational numbers and the irrational numbers. The loopful numbers, you can think of, I guess, just in your head as something really close to the set of rational numbers. So it's these guys here. So for this operator to be hypoelliptic, we're looking for these guys. We're looking for alpha as far away from the rational numbers as possible. And I guess we can arrive at theorems. So this is just to illustrate the how useful it is to have a theorem that that connects these two seemingly distinct concepts to each other. I haven't said exactly how we use a theorem like this to prove a theorem like this, but it follows. It's the most essential part in the proof of this statement is a theorem that's very similar to the Paley-Wiener theorem. So this is the kind of result we can get. We can characterize the hypoellipticity of operators with these kind of surprising statements. In this case, we characterize hypoellipticity by saying alpha is irrational and not a Liouville number. So it's a purely very algebraic kind of statement involving Diophantine equations. So that's quite surprising. Okay. So I guess that I'll stop talking about regularity now. And so at this point, then I guess we reach a problem, which is what if we encounter L, let's say a linear partial differential operator, and we prove that it's not hypoelliptic. Now let's say L is part of a differential equation, which we proved is solvable, and we would really like the solution to be C infinity. This is not hypoelliptic, but we really want it to be. Do we stop there and search for another problem, or can we insist further? Can we try to refine the notion of regularity of an operator to try to say it's regular in a certain sense, maybe, or to say that the solution is regular in a certain sense? And the answer is yes. We can refine this concept of regularity further and ask, okay, we have a U. Let's say the domain of U. Draw here. Say the domain of U might be this, and we want. So we know the operator is not hypoelliptic, so we have something like LU equals F, and F is in C infinity. We don't necessarily have that U is in C infinity. We don't necessarily have that U smooth, but we would like U to be something. So let's analyze U locally at a point, let's say x0. So this is a point x0. We've determined, let's say that it's not smooth there. So U is not smooth here. Okay, so U is not smooth here, but we would like to determine if it is smooth in a certain sense, and that sense would be in a direction. So we would choose a direction. Let's say this direction here, and we know by theorems of the Paley-Wiener type, which is this one up here, that there's a very tight relationship between the regularity of U and the decay of the Fourier transform. So what we can do here is we can take the Fourier transform along different directions of this domain. So let's say this is the direction xi1, and we'll take the Fourier transform of U here, and we'll see how fast it decays. And in fact, we can see how fast it decays around an open cone around Z1. So we can check how fast U decays in an open cone around this direction. And if it decays as fast as possible, we can say that in this direction, psi1, and at this point, at this chosen point x1, we have that u is, in a sense, smooth. So we don't know anything about these other directions here, but we can say that at least for this point and for this direction, if the Fourier transform along neighboring directions decays as fast as possible, then u is smooth locally, and we call this actually microlocally. Microlocal because not only are we restricting our attention to a neighborhood of x0, but we're restricting further, even further, to a cone, to a cone in the domain of the Fourier transform. So this is called microlocal regularity, and under these conditions we say that this pair of points x0, psi1, would not be in the wavefront set of the distribution u. Okay, so I think that's it for now. In the next video, I'll try to bring some more concrete examples and calculations on this wavefront set stuff.